Hello and welcome to the Platemaker Wizard tutorial 5. So we know the drill. Let's start Excel and we go into add-ins. We're going to put the program into tutorial mode. We're then going to go to the help menu. We're going to view the instruction manual, and then we're going to go down and select tutorial 5. And this is to do with plate standards and control, or page 3 of the Platemaker Wizard. So you need to read this background, but very briefly, controls tend to often be set in a separate area on the plate, and also controls tend to be plate specific. We tend to put the same controls on each plate repeatedly so we can calculate things like Z prime and other things in high content screening. Or if plate space is critical, then we might just stick the controls on the first or last plate. So it is much more convenient if there's a section in the program that allows you to define your controls independent of your experimental variables. Even though with linear linking, conceptually, you could define your controls within your experimental samples, it would just be a lot more hassle. Also, often controls have very different sample numbers to the experimental repeats, and so therefore it's good to be able to specify the repeat number for the controls. So let me show you how this works in the Platemaker Wizard and how I've provided this functionality to define your controls. So please read this section so you understand what we're talking about, and then we're going to pick up where we left off. So we're going to go and rebuild tutorial 4 final saved workbook build by using a template. So let's do that. So we flick across to Excel. We can close this now. We go down to here, create new data entry workbook. We're going to select tutorial 4 final saved workbook. We're going to say adjust template settings. We click next. So it loads the template. This is the template, the final template we were working with. We go next, 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 and preview. This was the template. And then you can see that if we go to the flat data file, we end up with this flat data table, which matches this. Okay. Now, if we look at the flat data table, we can see that it has no controls. But if we just look at the independent variable labels, we have both compound and dose. Now, let's have a think about what a control would look like. So in this experiment, we can think about two different controls. We can think about the negative control, which will be just the zero dose of any drug, or what we would call the vehicle control. So all these drugs are made up in DMSO, so the zero dose vehicle will just be DMSO. And likewise, we need a positive control. So the positive control would be a compound that causes maximum cell death. And one that is commonly used, that we've commonly used in the past, is benzathenium chloride at 100 micromolar. This causes maximum cell death, so it makes a really good positive control. So that's going to be our positive control. So obviously we have two components to the control. We have the name of the control, so it's either DMSO or benzathenium chloride. And we have the dose, it's either 0 nanomolar or 100 micromolars. So it means that if we're going to start adding controls, we're going to inject those values. We're going to inject the compound name into compound column, and we're going to inject the dose of the control into the dose column. So remember that, and you'll see how that works next as we do that. So we're going to click reject, and then we're going to go back to the dependent variable controls page. This is page 3, and now we're going to say use controls, and we now get this extra menu down here. So you can see that because there is only two independent variables, we only have two drop down lists, and the drop down lists you can see have the two independent variables, so we have either compound or dose. So let's select compound, and then let's select dose. And I've already said that the first control is the negative control, so we'll call that DMSO, and it's going to be 0, and it's nanomolar. And you can see that it's color-coded, so you can see that the 0 nanomolar is going to go into the dose column, and the DMSO is going to go into the compound column, which is what we want. Now, How many samples do we want? Well, let's have a look at our plate again. So if we go back to our plate map, which is here, you can see we're going to actually have 14 samples. And the reason why is because ultimately we're going to have our controls occupying the columns in the final build. And you can see we have 2 spare columns. So remember, with 384 plate, we have 16 rows, but we're excluding the edge rows, so that gives us 14. So we can, in theory, fit 14 positive controls and 14 negative controls. So let's do that. So we go back to here, we're going to stick 14 in here, and we click add, and our DMSO 0 dose 14 samples have been added. We now want to add our benzothenium chloride, and this is 100. And remember, it's not nanomolar, it's actually micromolar. So we select micromolar, we select add, and now we have our 2 sample controls in our experimental control standard section. So we're going to leave this as plate first and first plate only. We're going to click next. We click preview, and now you can see that when it builds this, we end up with this map, and you can see it's added controls on the first plate at the very top of the plate in rows, and that will match this one here. Now, this is not ideal because all that we've done is we've messed up our plate layout completely, because now we've pushed controls at the top and we've moved everything else down. We've made a complete mess. We now have sample 1 in plate 2 as well, and it's all a mess. So clearly we don't want this. What we really want is our controls in the separate plate area. So let's see how we do that. So I'm going to click reject. And if we look at the subplating area, we now have this extra box available since we have controls. And if we look at this box, it says control standards in separate columns or separate rows. And what that tells the wizard to locate the controls in an area which is separated from the rest of the experimental repeats. So we're going to put it into separate columns, okay, like this. And we're just going to leave it as so and push preview again. And now you can see we have put the controls into a separate area. So now they're appearing in the first 2 columns of the plate, which is great because they were 2 spare columns anyway. And so now you can see the first plate, all the area is now filled with samples, and we can see the controls are in the first 2 columns, and then the experimental samples start from column 4 onwards, and so it all fits nicely. And now you can see that sample 1, sample 2 and sample 3 of the experiments have now been restored in the way it was before. So that's a much better layout, and that's shown here. Now, one other thing to notice about these controls is, do you notice that we have here the DMSO clumped together in the top part of the plate and the benzothenium chloride clumped together here in the bottom part of the plate? And that is a completely fine layout. Although, again, if you think about the physicality of the experiment, you probably wouldn't lay it out that way. If you were laying it out with an 8-channel pipetta, you would probably choose to put all the negative controls in one column and all the positive controls in a second column. That'd be a much simpler way to lay it out. So let's do that. So we're going to click reject. And you can see that it says control standards in separate columns, but you can see the control layout direction can be independently set on page 5 from the experimental direction. So at the moment it's laid out by rows. Let's change this to by columns and push preview again. And when we do that, you will see that now the controls are nicely laid out. We have the negative control and then the positive control on plate 1 in the first section of the plate. So if we go back to our tutorial, you can see we've now done this one, and we've now changed it from by rows to by columns, and this is where you've got to if you're following the tutorial. So now what we're going to do is we're just going to explore some of the other options on page 3 of the wizard. So let's reject this, and we go back to the dependent variables control page, or page 3, and you can see that on page 3 with these 2 drop down boxes we have 6 different possibilities. We can either plate first or plate last on the plate, and we can either plate on the first plate only, the last plate only, or every plate. So in the tutorial, you can see that figure 93 shows 4 out of the other 5 options. Remember, there's 6 options. We already built the first one. The other remaining 5, it shows 4 of those. I'm obviously not going to show all 4 in this tutorial, but let's just move to the one that we want to use, and that's going to be every plate only. And what we'll do is, just for now, we'll move it to plate last just to show what that looks like. So that's just one of the options. And we'll click next. We click preview. And there we have it. We have now our plate controls being plated last on every plate. And that corresponds to figure 93D. Okay, so the next thing is, now the controls are located on the edge of the plate, but as we've mentioned a few times, the edges of the plate are not the ideal place for samples because of evaporation, which is why we have the edge rows and columns excluded. So if you want to really have your controls in the best place possible, it's best to have them on the center of the plate. And the Platemaker Wizard allows you to do that, so we're going to shift them back to the center, and the way we do that is we click reject, and then you can see we have a control offset. So this offset is, because we've got it in separate columns, this offset, the total will be the total number of columns that are available, which for this one is 20 because we've set it number 20, and exactly half of those columns would be number 10. So it goes from the left, so we want to move it in 10 columns, and that will center the controls. But what we're going to do now is, rather than push preview, we're also just going to go back to page 3, but we're going to go back using the previous key so we can see this page. So you'll notice that this is the equation editor page. We'll be covering equations in the next tutorial, but for the moment you can see we just have our 2 dependent variables. These are the only 2 that are available that we could use in an equation: cell depth and cell count. Let's go back one more page to the control page. And what we're going to do is we're going to put our cursor on DMSO 0 nanomolar 14 samples, and we're going to ask the Platemaker Wizard to calculate the average of this. And if we click calculate average, you can see now it says calculate average here. If we now click next, you will see that now we can include the average DMSO control in our calculations. So in fact, we're going to do that. You'll see in the next tutorial we have more advanced equations that we use in the demonstration workbook, but for this one we'll just keep it simple. So the 2 equations I'm going to come up with, the first is just going to be called cell depth, so it's percentage, and we'll just say adjusted. And the adjustment is simply going to be cell depth minus the average DMSO cell depth. So this is just subtracting off the 0 dose control. So in other words, whatever the background cell depth is in the untreated samples, that's just taken off the overall cell depth for each sample. So that's the first one. So we click add, and you can see now it appears this. The second one we want, we'll call it cell count adjusted, and this dimension is a number. And this is just going to be cell count minus, and again it's just average DMSO. Now you'll see the Platemaker Wizard is very clever. It can resolve which is the correct average DMSO to use. It knows it will have to use cell count average DMSO reading for cell count, and it'll have to use average cell depth DMSO reading for cell depth, but you'll see that in a little bit. So I click add again. Now the 2 new equations are in here. I click next, and I click preview, and now you can see we have a create equations section that's building, and there is our final build. You can see we now have the controls in the center just as we like. So this is very similar to our demonstration workbook that's shipped with the Platemaker Wizard. I can select accept, and if we go to the flat data worksheet, you can see there are controls at the beginning. You can see that because we asked for the average is selected here. So you can see it's averaging those 10 DMSO. But let's now explore how the wizard has used this average in our equations that we set up. And the way we're going to do this is if we move down, so we've done all this to this page, what we're going to do, there's the statistical summary, what we're going to do is we're going to set up these filters. Okay, so the filters we're going to set up is we want to set up DMSO average and docetaxel, so let's do that. So we go to compound, we want to set the filter DMSO average and docetaxel, like so. Then going to the dose column, we'll set up the dose filters, and for that we want to select the 0 and the 0.1 nanomolar. So we select those, and this gives us a much reduced version of the flat data table, which is shown here. And we can explore now how the Platemaker Wizard has created the appropriate formulas in the cell death and cell count adjusted areas. So for instance, if I go to docetaxel sample number 2, which is on plate 2, and I click F2, you can see that it's picked up the DMSO average of plate 2 in those 14 DMSOs. It's averaged, it's picked those up. There it is there, and it's subtracting that from the docetaxel 0.1 nanomolar, which is also on plate 2. Likewise, if I go to docetaxel 0.1 cell death adjusted on plate 3, you can see it's picked up the appropriate plate 3 DMSO average of the 14 plate controls on plate 3, and it's also obviously using the docetaxel sample 3, which is on plate 3, so it's done that correctly. And likewise, if I go to cell count adjusted plate 1, you can see that again it's picked up the, now you see how it's picked up the appropriate cell count. So because it knew this was cell count, it knew it had to pick the DMSO average of cell count, not cell death. And again, because that's located on plate 1, it's picked up the correct plate average on plate 1. So the Platemaker Wizard very cleverly matches the right appropriate control with the particular experimental sample that it's making this new calculation for. Okay, so that gives you an idea of how the control section can be used to create plate controls, and how also you can use averaging of the controls or maximum minimum and then use those in equations by using the Platemaker Wizard dependent variable equation editor. Okay, so that's that section. So what we're going to do now is move towards a more complex example. So the way we're going to do that is we're just going to go add-ins, create new data entry workbook, and this time we're going to select tutorial 5, a more complex example. We're going to adjust the template settings. We click next, 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 and we'll preview the build of that. And when we preview the build of that, we end up with this layout. And you can see the 3 cell lines. You can see that we have the different drugs. So it's very, very similar to the 4-well standard plate layout that we use with our different drugs. But notice that with this particular experiment, we have 3 different cell lines on the plate, and we also have it at different times as well. Now you'll also notice a subtlety. In terms of columns, we've excluded the edge columns, but we haven't excluded all the edge rows. Do you see that? We actually have only excluded the last edge row rather than both edge rows. And the way we achieve that, if we go back to page 5, you can see here we have excluded the outer columns, but the way we've excluded the outer rows is we've used subplating area, we've gone to 15 rows, and we've not used leftover space. So that's how we got just that single row excluded. So we need to take note of that. So if we now switch back to our tutorial and we move further down, that's explained here. What we're going to do now is this time we're going to repeat the process that we did before with compound and dose. So the same thing, we're going to have benzothene chloride and DMSO. And rather than use 14 samples, we're going to use 15 samples, which matches the 15 rows of the plate. So let's do that. So let's just follow that. So we go reject. We go over to dependent variables and controls. We say use controls. We select compound and dose. We're going to have DMSO 0 nanomolar 15 samples, remember, add, and then we want benzothenium chloride, 100 micromolar, add, next. And then when we get back to page 5, what we are going to do is select controls and standards in separate columns, and then we're going to select preview. So if you've done it correctly, you'll end up with these plate maps. Let's just go back to our instructions. Here they are here. And you can see it's not quite what we were expecting, because you'll see that although on page 5 of the wizard we have used a subplating area and excluded the last row, the controls are not affected by that subplating area. So the controls still will appear in the full plate. So if we switch back to the tutorial sheet, you need to read section 4.59 because it describes exactly how the algorithm, when you ask for controls to be put on a separate area, works out the number of rows or columns it needs to reserve in order to fit the controls. So for example, if you have a number of controls that would occupy 1.5 columns, by definition the minimum columns it needs to reserve is 2 columns. Likewise, if you have a number of controls that would only take up 1.5 rows, it would have to reserve a minimum of 2 rows. Or if you had controls that took up 2.5 rows, it would have to reserve 3 rows for controls. And whichever space is left is always left empty, because it will not put samples into the control area. So the one thing to point out is that when you say on page 5 to exclude the outer rows or outer columns, that is absolute. When you do that, that does reduce the plating area for the controls. However, it does not apply when you use subplating. So if you use a subplate and you say don't use the leftover area, the controls will still see the leftover area. So this is all explained here, and this is why, again, we're getting this space, because if you do the maths, remember we've excluded this last row, but we excluded it with subplating, so the control column area is a full 16, not 14 wells. We have 2 different controls, DMSO and benzothenium chloride. We have 15 of each, that means it's 30. So we have 30 controls. 30 is greater than the first 16, so it must reserve 2 columns. But of course, if we're reserving 2 columns, we now have 32 different positions, and that's why we end up with this gap of 2. We can also see what happens if we were to move the controls into a separate row. So let's do that. So we'll go back to here. We'll reject this build. We shall now move them into separate rows. And following on from the instructions, we'll also change the control layout direction from by columns to by rows. We push the preview key, and we now build the following workbook. And you can see that this time the samples have been located in the top section of the plate. And as explained in this section of the tutorial on page 137, the controls now take up 2 rows, although the second row is almost empty, because obviously you need more than 1 row to fit all the controls on, and so therefore the Platemaker Wizard reserves 2 rows, as described in this section here. Now, one important thing to note is there has been a subtle change to the plate in that you can see that now row P, which was empty before, has samples in it. And the reason why that happens is because, if you remember, we set the virtual plating area to 15 rows, or the subplating area to 15 rows. Now, there are 16 rows in the plate, so that worked when the controls are in the columns. However, when the controls are in the rows, because the controls themselves take up 2 rows, we now only have 14 rows to fit the samples. So because we set the subplating area as 15 rows, that is obviously greater than 14 rows, so the 15 is just ignored and all the rows are used. If we wanted to actually go down and have that same space, we'd have to go 1 less row than the number of rows minus controls. So the number of rows minus controls is 14, and so therefore one less row would be 13. So let's just do that just to show you. So if I change this to 13 rows, then you will see that this time we will get a layout which is similar to when we have the controls in columns, like so. Now, the next thing we can do is we can change this control layout direction from by rows back to by columns. And if we do that and click preview, you will see that now we get this pattern where both rows have empty wells, and that's obviously because it's plating by columns. Do you see that? So that's how that works. So if we go back to our tutorial, the next thing we're going to do is we're going to put it back to by columns. We're also going to have the control layout direction as by columns. Remember, we have to put this rows back to 15. Okay, so we put that back to 15 because now we don't have the controls in rows. And that will produce the plate map that we produced before. If we run that, that would produce this plate map here. But what we want to do now is we want to fix this little spacing here. So remember, what we've said is that the controls see the full plate. So one way to fix it would be just to put 16 DMSO controls and 16 positive benzothenium controls. Change it from 15 to 16. So let's actually do that. Okay, so the way we're going to do that is we're just going to go back to dependent variables controls page, and then we're simply going to put the cursor on the 15. We move that to 16. We push edit. We move the second one, benzothene chloride, to 16. We push edit, and then we click next, preview, and now you will see when the build has finished that the layout will have all the columns covered in controls. So let's just see that. So there you have it, all the layout is in controls. But the next thing to notice is let's have a look at these plate maps quite closely. So the first thing to notice is, remember, we've only specified the compound and the dose. We haven't specified the cell line or the duration. So this means that you can see that the controls take the value of whatever the cell line was when they start getting plated. And in fact, the first cell line in the list is PC9. So all these controls look like it's PC9. Okay, so these, you can see from the map that all the controls are labeled also as PC9. You can also see that on the flat data file here. Now, of course, this isn't ideal, because ideally we'd probably want this set of controls to be PC9, this set of controls to be healer, and this set of controls to be STC1. But there's something else that's interesting. Before we do that, just watch this. If I reject the plate layout and I go back to the dependent variables control page, and then I simply plate last, watch what happens when I do this. So I'm going to run the build again. And this time you can see that now the controls have come last. What is fascinating is that now you can see that the cell line is not PC9 anymore, but STC1. You can see by the color code here. And if we go to the flat data table, you can see that now, if we go all the way to the end, because remember the controls are now at the end of the plate, you can see that now they've picked up STC1. And the simple reason is because that was the cell line that was being plated when the controls are inserted into the plate. So what we want to do now is we want to fix it so that we also have the different cell lines for the control. So let's do that. So what we're going to do is we're going to reject it. We're going to go back to the dependent variables control page, and we're going to start the controls again. So this time I'm just going to unclick use plate controls. I'll get this warning saying, do you really want to remove all the controls defined for the experiment? We're going to say yes. We're going to click use plate controls again, and we're going to start again. So we already have our compound and dose. So now we're going to add the third parameter, which is cell line. Now you can see that in the flat data table, it would be cell line compound dose. We don't have to worry about the order that we put them in. We can put them in any order on the control page because it will match it to the label on the flat data column. So we don't have to worry about having the columns in the same order as the flat data columns. They can be in a different order on this page and they'll still match up when the Platemaker Wizard builds the workbook. So what we're going to do now is, again, it's DMSO and it's 0 nanomolar, but this time we're also going to specify the cell line, and the first cell line, as we know, is PC9, so let's put that in. Now, the other thing we need to think about, let's go down here because we're starting to work on this. The other thing we have to think about is how many repeats will we have. So we have 16 wells, but remember we're excluding the bottom edge, so that's 15. So we have 15 wells to play with, and we have 3 cell lines. So the number of sample repeats for each cell line to use is going to be 15 divided by the 3 cell lines, or 15 divided by 3, which is 5. So we put 5 in here and we click add. Then we need our DMSO again, and this time it's going to be the next cell line, which is healer. So let's put in the next cell line, healer, and we click add. And then the final cell line with DMSO is STC1. So let's put in STC1 and click add. Now, so that's the 5, but we're still going to have this problem with this space. Now, one way we could fix this is just to make STC1 6 samples, and then it will fit. But the problem with that is if you truly have not used the edge well, like the bottom edge, then you don't want to have data coming from that well, because that well won't be the actual sample. So just as we did on page 2 when we were defining our values for the independent variables of the experiment, here we can also use the spacer character to introduce appropriate spacers in our control set on the plate. So remember, the spacer character is a hash key, so we simply put the hash and then we click add. But remember, I've just put in as 5 samples. We only want 1 space, we only want 1 well, so let's change that to 1 and push edit. So we got back to 1, okay? And now we have to repeat the process, but this time we're doing the positive benzathenium control. So it's benzathenium chloride. Remember, it's 100 and it's micromolar. The first cell line is PC9, so let's put PC9. And we need to put it back to 5. We click add. The second one is benzathenium chloride, is healer, add. And the third one is benzathenium chloride, and it is STC1, add. Now, you might think that we could also put the final spacer in. We could do that if we wanted to give a final space. But actually, because that is the last control that is defined, we don't actually have to do that, because the space will just be left because it's run out of control. So we don't actually have to put in our final spacer. You'll see that in a moment. So we've now defined correctly our cell lines. So let's now click next and let's preview that. And when we preview that, let's see what we get. That now we have, in fact, our 3 cell lines. Now, interestingly enough, do you see what I've done here? I've actually used the wrong name for STC1. I've actually used STC1. So let's just fix that very quickly. So I'll just quickly fix that. So I go reject. I go to this one. I go to STC1. I need to change that to STC1 is how it's done. I go edit, and it's changed it there. I need to change it a second time, so just change it here and go edit. And now I'll run the plate again. And now I've got my naming consistent. You can see that the plate maps all are as expected. So we have now the controls with the 3 different cell lines, and we now have this nice space, so they all fit nicely. Okay, so the final thing I want to do with this plate is to move the controls into the very center, and also we want to get it to calculate the average. So let's do that. So we click reject. And this time, if you follow on the instructions, we're not going to push go to, we're going to push the previous key. So we push the previous key, so we can go back and see again defined equations. We're going to go back to here. We want to switch on the calculate average for the DMSO control again. So we're going to click on DMSO and we're going to click on calculate average, and you'll see it now switches on for all three of the cell lines because that is the controlling label, so that's the single group, but we'll discuss this a bit further when we build the workbook. We then click next, and what we're going to do now is we're going to build another example equation using this new DMSO average that we're calculating. So let's do this. So again, we're going to call this cell depth adjusted, and it's a percentage, and it's just cell depth minus average DMSO. We could also do the cell count if we wanted to, but for now, to keep it simple, I'll just have this single equation this time, just cell depth adjusted. So I click add, so there it is there. I click next, and now the final thing we have to do is shift the controls into the center. So remember, we have a possible 20 columns, so the center is 10, so we put it on 10, and we can click finish. And now you can see we have created our final workbook. We have our three cell lines, we have our controls in the center, and if we go to the flat data file, we have our DMSO average like we had before, and we also have the appropriate equations. We can look at this down here. So let's just look at this. So here's our equation build, here's our equations. Now the one thing to notice, however, is if we look at one of our equations, so let's just do that. If we again select DMSO average and docetaxel and 0 and say 10, you can see that this time if we look at the cell depth adjusted on the docetaxel, it is picking up the average, but if we look at the average here, the average is picking up the average across all the cell lines. So let me just show you that. Although this average says it's in PC9, it is in fact the average of all the cell lines, which of course is fine if you're happy with a global average, but of course it can be a problem if the averages for each cell line is very different. So if all your background for each cell line is fairly equivalent, then you could be appropriate just to use a global average across the cell lines for each cell line. But what you may want is a local average. So of course what you might want it to do is to calculate the background cell depth per cell line. So you want it to calculate this cell depth background in DMSO for PCE9 separate from the cell depth average for the healer cell line, separate from the cell depth average in the DMSO control for the STC1 cell line. Now, can we do that? Well, in fact we can. And if you go to page 148, it describes it here. And the way to do it is simply to create separate labels. So rather than just have one DMSO, you'd have DMSO H, DMSO P, and DMSO S. DMSO H is for healer, underscore P would be for PC9, and DMSO S would be for STC1. And in fact, I provided a template that shows you this. So if you want to pick up this template, it's called Figure 9 using multiple DMSO labels. So we'll adjust the template for this so we can have a look at this one. And if you go to the control thing, you can see how we've done it here. We've simply created three different labels, DMSO P, DMSO H, and DMSO S for the different cell lines. But as you can see, when you do that, you end up also having three averages, which means that not only do you have these three, but it means that if you want to do the calculations, you have to set up separately cell depth adjusted healer with that calculation, cell adjusted PC9 with that calculation, and cell depth adjusted STC1 with that calculation. Now, you need to read this section. All that works, but it's not very efficient, because what the Platemaker Wizard will do is it will create a whole section called cell depth adjusted healer, a whole section called cell depth adjusted PC9 and a whole section called cell depth adjusted STC1, but within that section only the combinations which have healer will be appropriate for healer. In other words, when you have STC1 like you have here, this says cell depth adjusted healer, but the background it's getting from here is from the healer cell line, but it's on STC1. So there's only going to be a third of the data in each of those subsections which is correct, and the other 2/3 will be incorrect. So the correct data is there, but you have a lot of incorrect data where you're subtracting the wrong thing. So can you actually fix that? Well, in fact you can, and the way to do that is if we just build this particular workbook as well. So I'll just quickly build it. And we go to the flat data file. The way we would fix this is we would go to our dependent variable filters. We would start with cell depth adjusted healer. And then what we'd do is we'd select the cell lines that aren't healer. So that would be PC9 and STC1. And we'd simply delete all these rows because these data are not correct. So this is slightly more faffing about, but it gets the same position, so we delete those. We then go back and select the next variable, which is cell depth adjusted PC9, and again we need to select the off thing. So for PC9 we obviously just want healer and STC1. We delete those. So this is actually not in your tutorial, this is just a bit of extra to show you how you actually do this. And then finally we'd select cell depth adjusted STC1, and we need to select PC9 and healer. We delete those. And then the final icing on the cake would just be to select maybe these three. And then we don't need this label anymore, we could just call this cell depth adjusted. And copy that back through to all the other rows. And that's it. And that is the final flat data table that you'd need in order to make this work if you wanted to do this analysis. So that is a little bit more complicated. Again, you may never have to do that. The other way to keep it simple would be, rather than using internal equations, remember the pivot table maker also offers powerful normalizations, which was discussed in the very first tutorial. Remember this normalizations tract. We have common normalizations here, including subtracting the first row, and getting rid of negatives, and subtracting the top row with no neg rescale. This might work in other circumstances. This way will not be sensitive to the problem of different cell lines because the cell line will be in the filter. This is quite advanced. If you haven't fully followed this, don't really worry. It's something you don't have to worry about if you're doing advanced normalizations. If you're just doing straight data analysis with the data, then obviously the pivot tables work fine and you don't have to worry about any of this at all. But this is just if you are interested in normalizing your data. Most of the time you can do it quite simply, but if you've got these quite complex layouts, you might just have to put some further thought into it. Okay, so that's that section. What we're going to do now is we're going to look at one other really important concept, and that is to do with what happens if you use a different injection order on the experimental control standard page. So let's do that. So rather than have to recreate everything, if we go to the create new data entry workbook, and this time we're going to select the template. I've already provided the template. It's faulty control column ordering example. So I click that, I click adjust settings, I click next. It has the exact same data as the one we had before, but this time you can see that the controls are set up differently. So this time I followed the order of the flat data table. So we have PC9, DMSO, 0 nanomolar. So the DMSO now is in the second column and the PC9, the cell lines are in the first, and this actually will build fine. So if I just click through and build the workbook, it looks exactly the same and it all looks fine. And in fact it all is fine if we just build the workbook. So let me just build it, and you can see it makes no difference at this point. Okay, so it's all built fine. It's exactly as we expect. This time we have the controls at the beginning, but exactly as we expect, so that's fine. Okay, but now what we're going to do is watch what happens if we now select to calculate the average of these controls. So what we're going to do is put it onto PC9 DMSO, and we'll click Calculate Average. And you'll see this time the Calculate Average appears both on DMSO and on benzoathenium chloride because it's linked, the two PC9s are linked. Now this is a problem because unfortunately these two are not the same, okay? So it can't calculate the average across two disparate type systems and bring them all together. And in fact you'll see that if I now click Next and I click Preview, I'll actually get an error when it tries to build the workbook as shown. And the error I get is this one. You are trying to apply summarization functions to your plate controls, but have not placed the name of each control in the first column where the controls are defined. You must do either of the following. Do not use any statistical summary functions on the plate controls definition page of the wizard, or reorganize the order of your independent column names so that the first column contains the actual control name that uniquely, and that's the important bit, uniquely identifies that particular plate control rather than an indirectly related independent variable. What it means by that, just to translate that, if we go back to resume and we go next, what that effectively means is this is why this first column is in bold. You'll see it's actually in bold, whereas the other ones are not in bold. It's because this has to have a unique control identifier. PC9 is not the unique control identifier, DMSO is. So this is why this will work if you don't use these statistical functions, but if you want to use these statistical functions, you must have a unique control identifier in that first column in bold. Okay, so that's an important thing just to bear in mind if you're doing this type of work. So now I'm going to cancel this workbook build. I'm going to go back to the tutorial, and the last thing we're going to look at is what it means in terms of sample repeats and plate replicates, how this relates to the sample repeats on the control page. So this is the final thing we're going to look at. So in order to look at this section, we're going to use one more template that has been supplied with the Platemaker Wizard. So we go Create New Data Entry Workbook. It's Tutorial 5, and the final thing we're going to look at is it's called Figure 109A. So you can see that we're imagining we have an ELISA assay, that we have two ELISAs, one measuring the EGFR receptor, the phosphorylation of the EGFR receptor, and the other one is measuring the total EGFR receptor, and they're in separate ELISA plates, and we're measuring each particular lysate in triplicate on the plate, so it's 3 plate replicates. But because the total EGFR receptor is done on one plate and the phosphorylation EGFR receptor is done on a different plate, plate replicate 1 of one plate does not match up with plate replicate 1 on another plate because they're different plates, so you'd have it as replicates, not as sample repeats. So we'll adjust these settings, we'll click Next. So you can see it's a very simple layout, a very small layout indeed. We just have 3 cell lines, we just have 2 compounds, and we just have 3 doses. This is the experiments. The control is very simple. We just have, the cell line is just called control. We have just DMSO, 0 nanomolar, but we have 5 samples. And as you can see, we just have the 2 different ELISA plates, phospho-EGFR and total EGFR. We then just have a single equation where we've calculated EGFR ratio, which is just phospho-EGFR divided by total EGFR. So let's just build that plate and see what we get. And when we build that plate, what we end up with is the same as figure 109A. So it's the same as figure 109A. And you can see that because if you look at figure 109A, the cell line map matches the cell line map, the repeat number map matches the repeat number map, and we have these 2 other maps which aren't shown here. This is why we have the lightning bolt break to show that this is a condensed version of the plate maps. So this is figure 109A, and you can see that the 5 controls, the 5 sample repeat controls, have actually been labeled as repeat numbers. So you can see this on the flat data file. You can see that they're repeat numbers. This is significant because if we now go to the flat data table and we just set the filter to DMSO, so we're just looking at DMSO, you can see that what has happened is we have PEGFR here, 1, 2, 3, 4, 5, total EGFR, and because it's assumed, the controls are assumed to be the same as the experimental repeats, in other words, we assume that there's no relationship between repeat 1 of phospho-EGFR and repeat 1 of total EGFR, the right way to calculate the ratio is to first of all get a single average of PGFR and divide it by a single number average of total EGFR to come up with a single number for the EGFR ratio, because there's no relationship between these different samples. In other words, sample 3 is not related to sample 3 on here. So that is the correct way to do that calculation. However, if we click reject and we now return back to page 1, and what we're going to do is change the plate replicates back to 1, and this time change the number of samples to 3. This would be more like a high content screening assay where you're getting this multiple readings from the same well, from the same plate. Then if we do that and we go back to page 5 and now we click preview, you'll see we end up with what looks like an identical map. So if we go back to our crib on 109, we now end up with this plate map. So this is figure 109B. You can see it has the exact same cell line map, but this time the repeat numbers have now all been moved in sample numbers. So the controls are now reading sample number, not repeat number. And if we look at the flat data table for this, and we look at DMSO, we can see what difference this has made. So you can see that now we have 1, 2, 3, 4, 5 sample numbers, 1, 2, 3, 4, 5 total numbers, and the EGFR ratio is now 1, 2, 3, 4, 5. And that's because if we go to, say, EGFR ratio 3, you can see that it's taken sample 3 PEGFR and divided it by sample 3 total EGFR. So it's assuming that there is a relationship between the first sample of PGFR and the first sample of total EGFR, which would be true if it was a high content screening assay, because obviously you get the multiple measured variables from the same well. The final question to ask, well, what happens if we do one final thing and we did set up an ELISA assay where we have 3 sample repeats and 3 plate replicates? And again, that is possible. And if you want to see how that's possible, if I just push the help key on page 1 and we go into the help key here, you can see it describes, again, if you want to read through this, it describes how plate replicates and plate sample repeats are handled by the wizard, which is what we've done there about how it handles it mathematically when it's combining different variables. But how you could end up with an ELISA where you have both multiple samples and multiple repeats would be in this situation, which is described in figure 2. And again, what we've done here is imagine we have one particular experimental variable where we're measuring one thing, but we've collected 3 independent samples of that variable. We've loaded that onto a plate, but then we've also, on the same plate, loaded it 3 times. So sample 1 has been loaded 3 times, sample 2 has been loaded 3 times, and sample 3 has been loaded 3 times. And now we're looking at, say, phosphorylation of EGFR over total. In that situation, both the sample number and the repeat number is 3, meaning that you have, for your overall independent variable, you have 9 repeats, but they're segmented into 3 from the Eppendorfs and 3 from the plate replicates. And in that situation, how does the Platemaker Wizard deal with it in terms of the controls? Well, let's have a look. So we'll go next. We click preview, and this time we're building a bigger plate. And now you can see this represents figure 109C. So you can see figure 109C, we have a much bigger cell line plate. In fact, uses up more than one plate. And this time in figure 109C we have both repeats and sample numbers. So in terms of our experiment, we have 3 samples, which is 1, 2, and 3 in triplicate. But if you look at our controls, we now have 15 controls, of which the 5 repeats that were specified on the control page, this has now been placed in the sample number, and it's assumed that those have been measured in triplicate 3 times, just as we did with our experimental samples. So that gives us 3 by 5, which is 15 overall controls. And you can see that if we now move to the flat data table and we select DMSO, you can see that now what we have is there are our 15 control samples segmented into 5 different sample numbers, and each of those sample numbers is measured 3 times on the plate. And so when we come to look at the normalization, the EGFR ratio, we still have our 5 independent samples, because in the samples you can relate sample 2 to sample 2, but the repeat numbers have first been meaned before the ratio calculated. So if I just pick DMSO sample 3 EGFR ratio, I click F2, you can see it's taken the 3 repeat numbers of sample 3, it's meaned those, it's taken the 3 repeat numbers of sample 3 on total, it's meaned those, and then it's calculated the ratio. And that is how it deals with the final possibility of multiple samples which have been replicated on the plate in, say, a ELISA assay. So I'll click accept, and that brings us to the very end of this tutorial. This has been a longer tutorial than some of the others, but hopefully it has given you some real insight into the powerful tools you have inside the wizard, which allow you to define plate controls and then use those plate controls in your data analysis. So if you're watching this tutorial on YouTube, please do like this video, and please think about subscribing to this channel so that the algorithm will make this tutorial available to more scientists who conduct work on microtitre plates. And until tutorial 6, I wish you all the very best with your experiments. Bye for now.